Hey everyone, Risk to Thrive and Survive. We are going to look at a total fallacy that anyone that uses any little bit of critical thinking can work out in their own mind that there's something big that's wrong here, and it's literally something big that is wrong. And let's get into it, and you'll see the fallacy of the eclipses and the sizes of everything that they've been trying to show us and how it just doesn't work. So we've been sort of looking at the sun in a sort of a flat kind of a way, because although we know they say it's a ball, when you talk about 93 million miles away, you get into sort of flat things. And we're going to see that's actually not the way to look at this. And it took a guy at ASU, Arizona State University, when we had a Flat Earth meetup, when Mike Ball was speaking to the planetary astronomer, I think that's what he called himself. He said something that was like a little bell went off my head. It was like, oh yeah, because when I spoke to him just a little bit, and I was trying to show him that you can't, from one light source, make a larger object smaller. And he got to talking about how, the sun isn't flat, it's round, and it comes off at all angles. And I'm like, oh, you just killed yourself. You just don't even realize it. So let's take a look at a couple things that they've been teaching us and see the huge fallacy. Now, when you look up the science of how the seasons are made on the Earth, you always get this. You get parallel rays striking the Earth. And the reason why, for example, 43 degrees is your angle right here at this part of the Earth is because the curve of the Earth is 43 degrees from parallel right here where it strikes at 90 degrees. If the sun came in at different angles, you could never calculate where the sun was on a curved Earth. It has to be parallel, and when you do the mathematics, I can't find the calculator. It used to be there. They probably took it down. But if you calculate the light coming off an object, even a flat object is what I assumed, at 93 million miles, it doesn't matter flat or curved, I think it's 89.986 degrees. So virtually parallel they have to strike. And here's another example. And why is this important? Again, for the seasons to work and actually for you to be able to measure where the sun is in the sky and to figure where your latitude is, the sun's rays have to always strike the Earth parallel. They have to. But what do they tell us? All of a sudden, there's a change when an eclipse happens. When an eclipse happens, this is what they show us happens right here. All of a sudden we have the top of the sun, rays suddenly come down, not parallel, but strike the Earth here and create this shadow. From the bottom of the sun, they come up, strike the Earth here. And this is why, I did a video called The Moon is 70 Miles Wide. And it's because during the solar eclipse, the moon's shadow on the Earth was only 70 miles wide. And people will say, oh, the partial eclipse, you have to count that too. No, there's no shadow on a partial eclipse. I'm sorry. The light isn't quite as bright, but there's no shadow. There is no shadow. You cannot see a shadow cross your area when a solar eclipse begins, and never you see a shadow unless you're in the total eclipse area. That's when you see a shadow. Let's get real and use what we actually observe, shall we? But here's the problem, right here. You see, no matter how far away the sun is, especially if it's farther away, and it's a ball, only the very little teeny part of the sun that faces the Earth would ever have those light rays strike the Earth. Has to be. If it's up here, it's on an angle going what? Let's see, out that way. It would never strike the Earth. What is it? There's some sort of rule for every 1 degree off at 60 miles. Is it? Yeah. If just 1 degree off, if you're walking, let's say, you want to go from point A to B, and point B is 60 miles away, and you're just 1 degree off, you'll miss it by a mile. All right. Now multiply that 60 miles, or take 93 million miles and divide it by 60, and what would you have if it's just 1 degree off? Well, I just did the math, and if you're just 1 degree off of parallel facing the Earth, by the time, since we're 93 million miles away, that light beam, all right, just 1 degree off of parallel from the Earth, which means just slightly off of wherever we are, center of the sun, would miss the Earth by 1,000,000 550,000 miles. And yet they have at the top of the sun and the bottom of the sun these rays crisscrossing all of a sudden to create the umbra penumbra. So only something like this would ever strike the Earth. Make sense? So in reality, it doesn't matter how big or small or far away, since it's 93 million miles, I guess you have to say that the exact size of the Earth is the only light rays we see, which means it's the same size, because all these other angles are going other ways. We'll never strike the Earth. We'd never see it. No way around it. So again, this is what we should see and what we've been doing. All right, this is how science shows it, except they show it a little different. Let's see how they show it. All of a sudden, see, this is how you would actually see the rays. They would come off at the different angles, never strike the Earth. All right, now they have them on top here. Instead of going up like this, they come down and they create this little 70-mile shadow across the Earth, right? So if the rays were truly parallel, you'd have this 2,100 roughly mile shadow during a solar eclipse. But they have to show it this way so that we get a little 70-mile eclipse. Okay, not the parallel like just flashed up there for a second. So let's continue. Here's another way they show it. This is a diagram from the how they were showing the eclipse, the Great American Eclipse of 2017. See, they have to have rays that are actually should be going up in this direction, coming down and making a very small shadow on the Earth. Sorry if my dog barking got in there. So Apollo supposedly went to the moon, and they took pictures, and you saw the Earth in the background. So let's see what kind of size of the shadow that should be cast, all right, when the Earth blocks the sunlight on the moon. So we're going to look at lunar eclipses here. So here we have Apollo. Here's an Apollo astronaut somehow in the vacuum of space with his 12 layers of cloth, machine and hand sewn, holding at the vacuum of space, and or holding in his pressurized suit from the vacuum of space. Another video on that coming up. And here's the Earth. Wow, what kind of shadow do you think that would cast on the moon if it was blocking the sun? I mean, there's the arc. We should see the size of the arc of the shadow on the Earth, right? I mean, on the moon during a lunar eclipse. Let's look at actual eclipses and see what we see. And remember, because the sun is far away and we get these crisscrossing solar rays, we get a smaller shadow. So when you reverse it, it's still the same distances. You just put the Earth in front of the moon. The Earth should be casting a smaller shadow than even this. Well, let's take a look at an eclipse. Here's an eclipse, and this part right here is the Earth shadow, right? We're going to see it before it turns colors also, because people will argue, oh no, you got to look at it the other way, Rich. I'll tell you, cognitive dissonance just kills everybody. So I did a little arc here to match it up, right? See how it matches there? And that's, let's see the size. There's the size. Size of the Earth. How come it's not smaller? Look at that. And I squeeze it down a little bit because I do have it a little bit elongated. Move it over, and it matches pretty well. Really does. So we have the Earth isn't casting a smaller shadow, but the moon does. Should be no difference. Really should be. And from that picture of the Earth in Apollo's picture, does this look like the size of the shadow should be cast? I think not. So here is a time-lapse photography of a lunar eclipse in 2017. And let's watch the shadow come across. All right, it gets a little bit better defined as it gets further. Notice this right, I'm going to go back. Notice this oscillation. We always see this oscillation in eclipses. So I always say, I guess the Earth is jumping back and forth in space. Anyway, I get to the point where it's really dark, so we can do another little arc to see how it should work. There we go. And now there's no yellow, there's no umbra penumbra mixing here. We just have the Earth shadow, right? Look at the arc of that. All right. Now let's put it on. Look how big that is. Unreal. Earth doesn't get smaller, but the moon does, huh? That is a huge circle. So the Earth should have taken up pretty much the whole sky in that Apollo with this size shadow. Do you see the big problem they have? If you have an umbra penumbra, which is the only way they come up with colors in the shadow, which is impossible. Nobody can demonstrate colors in a shadow. Can't do it. Can't cast a shadow with color. Doesn't exactly match that, does it? So there's the big problem. Just use a little critical thinking, and this is what we come up with. And there's just one thing I want to add real quickly for the unbelievably skeptic non-thinkers. You can use the exact same 93 million mile away sun that the Earth and the Moon do to create the umbra penumbra, supposedly. Go outside with a ball that is 4 times larger than another one. You will then have a ball that represents the Moon and the Earth, and take the Moon and try to, the smaller ball, cast a shadow using the sun. Go at noon when the sun is lined up so you got 90 degrees overhead or close to it, and try to get the Moon to, the smaller ball to cast a shadow on the Earth, the ball that represents the Earth. Try to get that shadow that's cast on there to be smaller than the blocking object itself. You got the exact same sun. Try it. Reverse it. Do what you want. I've done this over and over. You can't do it. The shadow will be the same size or larger every time. Every time. People say, well, the sun's rays in the atmosphere, Rich, it's scattered. Yeah, well, that's even better for you, for your side, because it throws the light out, makes it larger, casts it all in different directions, right? That's what they say makes a smaller shadow, is when the light is diffused in different directions or a larger object. So it's all for your favor. Go out and try to do it before you poo-poo this. You can do the actual science yourself. I've done it. Find out what exactly is going on, which is we've been lied to. NASA's big problem. Take care, guys. God bless.